Hi, everybody, and welcome back. It's Kira Garfolo here with Greenville Tech in Math 109. Today, we're going to talk about section 2.2, which is fitting lines to data points. We'll be modeling linear functions. To talk about these functions, we need to talk about the ideas of exact and approximate linear models. If data points fall exactly on a line, we can say that we have an exact linear model. You can think about this as looking at a scatter plot where every single point is on that straight line. Our textbook talks about a piece of uncooked spaghetti. You can also think about using a ruler or any other straight edge that you can think of. If you put a straight line down on your graph paper, every single point that you've plotted falls right on that line somewhere. To assess whether a model is exact, we also need to talk about the concept of first differences. So first differences is a fancy word for saying how much did Y change. We need to look at the difference between each output, so each Y variable, at each different step compared to its previous value. Let's look at this a little deeper. So assuming our data set has uniform inputs, and that means that our X values are increasing in uniform ways. So it's the same step from one X value to the next X value to the next X value. So you might be going up by 1 unit at a time. You might be going up by 2 units at a time, 10 units at a time. However you're going up, it's the same number of increase each time that you move a step up. A linear function fits the data exactly if our first differences are constant. So if every time we increase a step on X, we increase the same amount on Y each time, this is going to be an exact linear model. That means that our rate of change is perfectly constant. So each dot goes up by exactly the slope every time. Now, if the first differences are almost constant, so they're not the same number, but they're bouncing around a little bit, but they're not all over the place, they're still somewhere around the same ballpark value, then we say that we have an approximate linear model to fit the data. Let's look at some examples to help make that make sense. It's a little easier applied than it is explaining for some reason. You'll notice that a lot of times in Math 109 and other math classes. So here in this first example, we set our X values, so our inputs are 0, 5, 10, 15, and 20. We have that uniform input because we're going from 0 to 5, which is 5 points, 5 to 10, which is 5 points, and so on. We're going up 5 each step that we go. Now, if we look at Y, we go from 7.5 to 12, which is going to be a 4.5 point increase, and then 12 to 16.5, which is a 4.5 increase. 16.5 to 21 is also 4.5, and 21 to 25.5 is also 4.5. Now, the first difference is always blank for the first observation because we don't have a previous value to compare it to. So it's these 4 that we're interested in. And as we noted, they're all equal to 4.5. Since this 4.5 stays constant, we say that we have an exact model, an exact linear model to fit this data. Now let's look at another example. Here we have X as 0, 2, 4, 6, and 8. We have that uniform input again because we're going from 0 to 2, 2 to 4, 4 to 6, and 6 to 8. So we're going up by 2 points each time. And so we're ready to look at our first differences. Here, our first difference here is 1.2 minus 0.8. So it goes up 0.4. And then 1.2 to 1.5 is only 0.3. And 1.5 to 1.9 is again 0.4. And 1.9 to 2.25 is 0.35. So looking at these differences, we see they're not all identical, but they're not far apart, right? They're all somewhere around 0.35. They've bounced down to 0.3, 0.4, but they're all reasonably the same. So here we would say that we have an approximate linear model. Now, again, I always encourage you to check for the uniform input first, because if you don't have the same distance between each X value, it's not going to make much sense to compare the Y values the way that we've seen here. Now, in the case of approximate fits, finding the line of best fit can be a bit tricky. We can do it visually by just eyeballing, right? We can throw a piece of uncooked spaghetti like the text says, or throw a ruler down, or just kind of freehand a straight line that'll go through as many points as possible, but also kind of centers in the data. It's a visual guess, but there are a lot of correct visual guesses. If I had everyone in this class, if I gave you this graph without the straight line through it, and I said, hey, draw the line of best fit, you'd all draw close to the same line, but I doubt that any of you would draw exactly identically the same line. So when we estimate this line, you're just going to kind of do exactly like I said, you're going to draw that straight line edge. If you want to write an equation for that line, so you're going to approximate it and write the equation for it, then I would encourage you to find 2 points on that line and find the slope and then use point slope form. If you needed to, you could solve for y and put it in slope intercept form, but that would give you a good equation for this line that you're best guessing at. Again, if there was no other guidance, you guys would probably all come up with slightly different models. They'd be similar, but they wouldn't be identical. So how do we find the truly best line? Instead of just guessing, how do we let math do the work for us? So there are many good fit lines for the data. All of the ones you guys would have likely drawn would have been decent fits, but how do we know what's the best? Well, to get the best, we would want to do this every time for any of the good fit lines. We would want to measure the distance from each point to the line itself. This would be called the error term. Since we're going to be on either side of the line, some will be positive and some will be negative. So we'll square these distances, and then we'll do that for every point, and we'll sum the squared distances. Now we need to do that and get a new sum for every possible best line. So you can imagine that this would be long and tedious. You'd be drawing lots of lines, you'd be taking lots of distances, and you'd be finding lots of sums. Then what you want to do is choose the model with the smallest sum of squared distances. So basically those errors that you squared, whichever one has the smallest of the sum of errors is going to be considered your best model. This method is called the least squares method for linear regression. And me as a statistician, this is something that I use all the time. So this is a section that I really like to teach. The good news is we won't do any of this by hand, but our calculator will do it for us. So you won't be asked to guess the best line, to find the sum of squared errors or any of that. But if you see that at any point, and some of it comes into play if you're using regression in software, that is where it's coming from. So here are these instructions mainly for reference, but we'll talk through them and then we'll walk through an example and I'll show you the screen. On your 83 or 84, the first time you do this, or anytime you reset your calculator or get a new calculator, make sure that you adjust your settings. You won't have to do this every time, but it's a good idea to check now if this is the first time you're using this for our course. So you're going to go to Catalog and you're going to select Diagnostic On and press Enter. I'll show you that here in a second. Then, if you've already done that, or this is the second time using this or any of that, you're going to enter your data into L1 and L2, just like we did when we were making those scatter plots. You're going to press Stat, Calc, LinReg, and you also want to store your regression equation to Y1. You're going to do that using the Variables button, and I'll show you how. When you select Calculate and press Enter, it's going to spit out your regression equation. It's going to give you some other information too that we'll talk about. If you want to see the line plotted with your points, you can use Stat Plot to turn on plot 1, just like we did to see those scatter plots before. And then when you use Zoom Stat, it's going to show you the graph with your points and with the line of best fit on top of it. Let's do an example here. We're going to do this example. It comes from our text. We want to find the equation for the line of best fit, and we also want to take a look at it on the scatter plot. So I'm going to get out of here and bring us to our calculator here. So in our calculator, The first thing we want to do is check for those diagnostics on. Catalog is the same as the 0 button, but we just have to press second. So we get a second catalog, and we need diagnostics on. Now remember, this is alpha locked, and there is a D button right here. So that'll save us some scrolling. We're going to scroll all the way down, and we see diagnostic on. When you see that, press enter. And that is going to give you what you need. When you press enter again, it's going to do it for us. Now, I don't know where it went, but let's see if I can reload one. Okay, so I might need to double check and make sure that my diagnostics are on. Of course, it doesn't want to work. Why is this not working today? Okay, so our diagnostics are on. Sorry for that delay. This seems to be happening to a lot of faculty today, and I don't have a document reader in my office to switch over to that and use my real calculator. Okay, so once we have this, we want to input our data. So we're going to go to Stat, Edit, and we want to enter our Ys. So we have 20, 25, 30, 35, 40, 45, 50, 55, and 60. Now we need to put our Y values in. So 37.2, 38.2, 39.2, 39.8, 40.4, 41, 42, 42.9, and 43.6. Want to double check and make sure we didn't make any typos. Make sure that we don't have any extras on the X or extra on the Y. So now, to get our line, please pay attention here. Make sure you use the stat calc, not the calc that we use on the graph. They do very different things. We're going to press stat, and we want to scroll over to this calc. And when we look here, option 4 is linreg AX plus B. The X list is L1, the Y list is L2. That will stay the same as long as you did X and Y in L1 and L2, which you should. We're going to ignore the frequency list. And we do want to store our regression equation in case we want to use it later. We'll see that later in the course where it becomes useful. So we'll press this vars button, and we'll scroll over to yvars, press enter, and press enter. We want to say, we want to save it as Y1. Scroll down to calculate and press enter. It's going to think for a second, and then it's going to give us this output. So remember, we have AX plus B. So here, A is our slope. You can think of it as MX plus B. And our slope here is 0.155. And B is our intercept, which is 34.278. That is our model. And you can see that it stores it here as 0.155x plus 34.2777. So when we told it to store, it's going to put it as Y1 so that we can easily graph it. Now we need to go back and turn our scatter plot on to look at it. So we go to stat, not stat. We go to stat plot, so second Y equals, and we want to turn that first plot on. And then we can go straight to zoom And we can tell it, we'll scroll down until we see Z plot. Let's use zoom stat. So we'll use number 9. And that is going to give us all of our points, and it's going to give us our line on top of it. So we know that this straight line has the equation y equals 0.155x plus 34.278, roughly. And these are the points that it used to get that from the regression equation. We go back to our PowerPoint. We can see that I've typed these for later reference for you. Please make sure that you take a few moments and make sure that you can replicate these results. This is something that will come back to haunt you if you skip over it entirely. Now, just as a side note, our scatter plots are considered discrete data. We have certain values of X and certain values of Y that are given. They represent discrete data points. So they're little points that are finite, they're countable, and you can see their values. On the other hand, when we draw a line, we're talking about continuous data. Remember, there are infinitely many points on any straight line. When we're doing regression and we're finding that line of best fit, we are applying a continuous model to discrete data. Usually that's not going to be a big deal, but sometimes we have to stop and think about our output and whether it makes sense. For example, if we're going to use something to predict, if we're going to use that line to predict other values, it wouldn't make sense if we have only something that's whole numbers. So we were predicting, number of ice cream bars sold. You wouldn't predict 16.2 ice cream bars. You would want to round in a way that makes sense so that you get a whole number. Now that line is great, but how do we know how good it actually is? When we looked back at our example back here, we can see here that that's a pretty good looking fit. Those points are all pretty close to the line. I'd say it looks good, but me saying, hey, it looks pretty good is fairly subjective. What do we do to get an objective numerical measure of fit? We can use something called the correlation coefficient. This is statistics 2. So again, my favorite section. We have the linear correlation coefficient that we represent by R. It is going to tell us how well that model fits. R can be positive or negative. If it's positive, it's talking about an increasing slope line, and if it's negative, it's talking about a decreasing slope line. So the sign itself doesn't tell you how strong the relationship is or how good the fit is. It's just telling you which way the line is pointing, up or down. The closer R is to 1 or -1, the better fit. The closer R is to 0, the poorer the fit, okay? So an R equals 0 means that there is no good fit. Those lines are just randomly scattered all over the place. If we have an exact fit with an upward slope, we'll have R equals 1. And if we have an exact slope with downward slope, we'll have R equals -1. In our example, it is output in the calculator. If we go back here, we can see it's right here. That's part of the diagnostics that we turned on. Be careful, we're not talking about R squared. That is something else in statistics. Our course is only concerned right now with R equals 0.997. That's awfully close to 1, and that is an excellent, excellent fit. Some graphical examples to help you in case you're struggling here. R equals +1. Again, we have that straight line up, and every point is precisely right on that line. The same thing over the other end, R equals -1. Every point is precisely on that line. It's just pointing downwards. For R equals 0.8, it's still a strong relationship. We can still see that that's a good line of best fit, but the points are bouncing around a little bit. It's positive because it's pointing up. Now, as those points start to be not nearly as helpful or meaningful, right? So our line doesn't really help explain it nearly as much. We get much lower R. So we get R equals 0.3. Here's an example of R equals 0 where there's no good linear relationship whatsoever. We just draw a straight horizontal line. Our model doesn't really do anything to predict it as Y is changing, or as X is changing, Y is just doing its own thing. And then these are the cases on the negative. In general, if you look at the absolute value of R, the closer that absolute value is to 1, the better off you'll be. Now, especially if our model is a good fit, we may want to use it to predict other values. If you're making a prediction between existing values, you're using interpolation. And if you're making a prediction outside the range of given data points, you're using extrapolation. So interpolation is within the bounds of the graph. Extrapolation is outside the bounds of the graph. So if you have data from x equals 5 to 10, and you made a prediction for x equals 7, since 7 is between 5 and 10, you're interpolating. If you made a prediction for x equals 12, then you're outside that 5 to 10 range. So now you're going to be extrapolating. Now make sure that you can try this section for yourself. Definitely work through our example and try it out. You can use my advice as a guide, but definitely get to the point where you can do it without my help, because on the test you won't have these slides to help. Practice again with our first example. So remember, we had that first example with an exact fit. You can find the regression equation for there, and you should see that R equals 1, because remember, it was an exact linear model. Remember here that practice makes perfect. You have unlimited attempts on your homework and unlimited attempts on your quizzes. So practice, practice, practice. If you need additional help, remember that there are resources all throughout the Blackboard shell for our course. There's departmental resources, there's additional resources from me, tons of additional resources from your text. Within the departmental lecture notes, there are small short videos embedded that can be helpful to many students. And also remember that the Math Center is available and that my office hours are available. Don't let yourself fall behind. All of this is used for the rest of the course. And take your time going through it. Make sure that you are doing your homework. Make sure that you're getting that practice, and you will do great on any tests or quizzes. As always, if you have any questions, you know how to reach me. Shoot me an email or stop by and see me during office hours, and have a great day.